genius. And one day he came out with an amazing puzzle. And he announced, it cost $10, but he announced the first puzzler to solve it, the first person to solve it, will be awarded $10,000. Okay, what was the puzzle? Here it is, this is the puzzle, and you have to take it apart. You have to separate the two pieces. Now, the first thing you ask when you see such a picture of a puzzle is, what is it made of? Is it rigid, is it made of metal, or is it made of string? Is it flexible, right? So I'll answer by showing you the original. I have the original here. Okay? So here it is. It's made of string. Okay? So and you're supposed to be able to take it apart. Well, people bought it. Many people bought it. It became very popular. Hundreds of thousands of people bought it. He already passed away, and his children continued manufacturing this amazing puzzle, and then his grandchildren, but no one ever was able to solve the puzzle. Okay, so one day they were preparing for the 50th anniversary of the invention of the puzzle, the Jubilee, but there was this puzzler union, probably the IPP, who started doubting. They said, well, maybe this was all fraud all along, and they decided to sue the heirs, the grandchildren of Mr. Genius. Okay, and so like a representative act for $1 million for representing all the people who were ever bought the puzzle for $10 and actually it was a fraud. Okay, that's what they thought. So they went to trial. And, well, it was very simple. The judge said to there was the grandson, Genius Jr., and the judge said, well, come into my chamber and show me how you solve the puzzle, and then you don't need to pay $1 million. So, but the Genius Jr. said, well, Granddaddy never told us how to solve the puzzle. He just told us how to manufacture it. You open strings, you start with an open string, you close it, and then you weave the other one into it, and that's all he taught us. He never taught us how to solve a puzzle. And, well, it's a hard puzzle. And it takes a long time, maybe it take 100 years, 200 years, until a very, very smart person will come along and will be able to solve it. The fact that 50 years no one was able to solve it doesn't show that it cannot be solved. So the judge thought for 20 seconds and he said, I agree. The fact that 50 years no one was able to solve the puzzle is not proof that the puzzle cannot be solved. So he came to the representative of the puzzler union and he said to him, well, this is what I require from you. You have to prove to me that the puzzle cannot be solved. I'll give you 3 weeks. Our next meeting will be 3 weeks from today, and you'll have to prove to me that the puzzle can't be solved. So the question is, if the puzzle cannot be solved, how can we prove it? So this is what I'm going to speak about. So the people who they had to seek advice from were people who work in knot theory. Knot theory is an area of mathematics which deals exactly with such closed strings. It could be in one piece or two pieces. So you have a piece of a string here, a closed loop, one or two intertwined, and some knot in them. So what is a knot? A knot is exactly what you see in the picture. No more, no less. The only thing I need to say is that it's made of flexible material, not out of metal, but flexible material. So here's an example of a knot. And the typical question would be, so since it's flexible, when I change it like this, it's still the same knot. I call it the same knot. It's not a fixed object, it's a flexible object. So if I do this, this is still the same knot, this is still the same knot. Anything I do with it, I consider it the same knot. That's obvious if I have a flexible string, so I could have maybe some other knot. And the typical question in knot theory would be, are these the same knot? Can I play around with this and finally get to this? So if I can, I just have to show you that I can, right? But if I can't, the question is, how do I prove that I cannot? How do I prove that I cannot? So what are knots here? So here, for example, there's knot, here's a knot, and here's another knot. We already understand what knots are. Here's another knot. The simplest knot is called the unknot. It's just a closed loop, which is not knotted. Its name is the unknot. And then we can talk about two-component links, like the puzzle of Mr. Genius. And here's another two-component link. And if you remember the picture we had before, so this is exactly the puzzle of Mr. Genius that we need to prove, or either manage to solve it, to separate it, or prove that it cannot be separated. So here's an example of a three-component link. And here are many different links, knots and links. You can see if it's one component, a knot, what we call a knot, you can see one color, then it starts with two colors. So I have something here. Two colors, you can see it's two components, and here the beginning of three components. Okay, so people are interested in such objects. Mathematicians are interested in such objects, and very heavy machinery of mathematics to study these objects. Okay. So here's the knot, and our main tool to understand the knots is a knot diagram. What is a knot diagram? Exactly what you see. You have a knot. This is a three-dimensional object, a flexible three-dimensional object, and then I project it onto the plane. I project it, I decide how once and for all how to project it onto the plane, and you get a flat picture like this, in the plane. And usually this, the overstrand is continuous and the understrand is broken under it, so this is the way we usually draw a diagram of a knot diagram. And the same knot obviously has many different diagrams. I can play with it and now make a different projection, and play some more and make a different projection. Different projections, these are different diagrams of the same knot. So the first question we want to understand is, how can we know that two different diagrams are diagrams of the same knot? What is the relation between different diagrams of the same knot? So this was figured out many years ago, maybe 100 years ago. So let's see what could happen along the way. So it starts moving, and we follow the projection. So something like this happens, something like this happens, something, and so on and so on and so on. And it turns out a mathematician named Bar-Ilan, maybe 100 years ago, realized that, proved, of course, that there are particular things that can happen along the way. So let's follow what we had before. The first thing happened around here, and this you can see back and forth, sometime like this. A loop can appear or disappear. This is called Reitermeister move number one, the first Reitermeister move. Okay, so here's like a big drawing of the first Reitermeister move. A loop goes in both directions. A loop can be created or disappear. Let's see another thing that happened. What happened here, around here, is something like this. You can see it back and forth. Obviously, this is something that you can do. And this is called Reitermeister move number two, the second Reitermeister move. And this is a big drawing of the second Reitermeister move. Okay? It goes in both directions. And another thing that can happen is what you see here. Flipping back and forth a little bit. These three moves are all that can happen. If I have two diagrams of the same knot, I can always move from one to another by a finite sequence of these three moves. If I deliberately want to do something more exotic, I can. I can have 10 strands passing the same point at the same time, all kinds of things, but I don't need to do it. I can always manage to do it for any two diagrams of the same knot. I can always manage to come from one diagram to other diagram by some finite sequence of these three Reitermeister moves. Okay, so the next thing, after I understand this, the next thing we're going to do, we're going to attach some number to every diagram. I'll show you how to compute some number from the diagram. But the important thing is that we'll show that when we pass a Reitermeister move, this number doesn't change. When we pass another Reitermeister move, it doesn't change. So if I have two diagrams of the same knot, then this number, the number we attach is the same number, because first of all we said that any two diagrams of the same knot, we can pass from one to the other by some finite sequence of Reitermeister move.